Okay, well, thanks very much for the introduction and for inviting me to this presentation. This all came from our national SFC meeting last August, where the topic was really non-stationarity and how the various councils are dealing with the non-stationarity that we observe in our fisheries. And so my presentation today will really be in two parts. The first part was a case study that was presented by my colleague Connor McManus, and it was really talking about a number of stocks. I have to get back to the beginning here of my presentation that we are dealing with in the New England region, and that we notice have their productivity has changed, and we have to try to adapt in sort of ad hoc ways. And so I'll work through this case study of winter flounder. I think that really sets the stage for this stock, but other stocks, and then how we're searching for solutions with a more codified way of dealing with these changes that we observe. So here's the southern New England mid-Atlantic winter flounder. And it has been historically a significant species for both commercial and recreational harvest. And the winter flounder in New England is managed as multiple stocks. You can see the stock delineations here. Starting from the south, we have southern New England. Obviously, winter flounder don't occupy all these statistical areas, but they're closer to the coast. We have the Georges Bank stock, which I'll be talking about in the second part of my talk, and there's a Gulf of Maine stock. Winter flounder spawn demersal eggs in the winter and the spring, now, basically, within estuaries and coastal waters. And because of this estuary dependency, it's actually a meta-population of individual stocks. We have studied the winter flounder population in Rhode Island in great detail. I hate to say this, but we've almost studied them to death because through our various surveys, we know the stage-specific abundances from egg all the way to adults. And we can say with some confidence now that Connor said it's considered to be vulnerable to climate change. We know the winter flounder is vulnerable to climate change, and we know what the mechanism is, and we'll get into that in a minute. Here's a graph showing the time trajectory of the spawning stock biomass for winter flounder, and you can see the decline to the present day. And as of the 2016 assessment, you can see that the SSB target was up here at 60, the threshold was there at around 30, and so the stock was clearly in an overfished condition at that point. If we look, this overlay here is really trying to show that fishing mortality had been high in the early years, but since had been reduced to low levels. So we would say that the stock was overfished, but overfishing was not occurring at that point. And so winter flounder was under a rebuilding plan. Switching the environment, it's known that there's a temperature winter flounder relationship. So if you look on the left here, these are the winter temperatures for estuaries along the coast. So we have Buzzards Bay, Narragansett Bay, Long Island Sound, Delaware, and Chesapeake. And you can see that they share the same temporal patterns in temperature, although the magnitude of temperature is different. Going from Buzzards Bay, you can see the scale is lower here than in Chesapeake Bay. And so as a result, we also see synchrony in winter flounder, except that for the more southern stocks, they're really kind of getting below the detection level. So although you see synchrony for some time periods, these southern stocks, the winter temperatures are just too warm for successful recruitment of winter flounder. So this is based on work of my colleague, Rich Bell. And he's taken this further. One way he did it was to fit time-varying stock recruitment models showing that there's a decline in productivity over time. And when he fit this state space model, he actually got results that were consistent with the stock assessment. So it seemed like including changing stock productivity in the stock assessment is consistent with the data that we collect. And basically, warmer waters are found to negatively influence stock productivity. So the next step Rich took, this was in a follow-up paper, he made projections of winter flounder by taking the climate projections you can see that the different climate models and the ensemble mean here, projecting increasing temperatures in New England up until 2050, and then simulated the winter flounder population under different scenarios. So the first scenario, the blue one, that's the base case. There's no fishing and there's no climate effect, and we would expect the winter flounder population just to recover marvelously. And so that would be a very optimistic scenario. The second one is the yellow, where the environment is included as a change in productivity, but it's basically saying, well, productivity is low and we don't really think that it's going to improve. In which state the probability of rebuilding is very low or nil. And then finally, get a temperature dependent model in which the stock was able to recover till about 2030, at which point the temperatures are just too warm and the stock would decrease again. Sorry, just recovering from a cold. And we've done more studies like this for Narragansett Bay, and it just seems like there's a very low probability that the stock could recover with increasing temperatures. So now we get to the management track assessment. In the 2022 management track assessment, there was a decision to truncate the recruitment time series to more recent years to reflect the more recent environmental conditions. And this was based on the assessment of temperature time series from Bell et al., what I just showed you, that temperature recruitment time series. Also, regression tree models suggested a split in recruitment time series at 1990 and 2002, which I'll show you. And so the decision was made just to have a recruitment window, to use the last 20 years of recruitment to inform the projections moving forward. And so this shows that recruitment window. These are the historic recruitment data. You can see recruitment was high up until the year 2000, much lower since then. And this is showing the temperature. And the rationale was that since 2002, the temperature has been above 5 degrees Celsius, and that's known to be the condition that it is detrimental for winter flounder recruitment. So that was the recruitment window that was chosen. And so based on this, if you project these recruitment data forward in time, it leads to a lower estimate of a BMSY. And so with our revised reference points, we can see that now this is the fishing mortality rate. The stock is not, overfishing is not occurring, and we've moved down the biomass reference points. That's the BMSY, it's right at BMSY, and that would be the overfishing threshold. So then the council decided, well, the stock is not overfished anymore and overfishing is not occurring, and it was considered rebuilt, and we're just managing as if the stock were rebuilt. So effectively, we basically moved the goalposts for winter flounder. So when the SSC met to set the ABC and OFL, you can see that these is the historical historical ABCs. It resulted in an increase in the overfishing level and in the ABC, which seemed very counterintuitive for a stock that was overfished. Why would we be increasing the catch over 4 times the current catch? And so that was really a dilemma. And the reason this occurred is because the assessment had adjusted the BMSY, but it had left the fishing mortality rate unchanged, either at FMSY or you can see 75% of FMSY. And so the SSC deliberated. We basically said that instead of using the default 75% FMSY, we would reduce it to 50% of FMSY held constant. That's this scenario here, to account for the fact that we believed that the productivity of the stock had declined. So that was a rational decision, but it deviated from our agreed on harvest control rules. So moving forward on this, we see this not only for winter flounder, but we see this for an increasing number of stocks. And so it led to some more general questions about when should we update our analyses? Like, when should we change the recruitment window? How do we rationalize these breakpoints when we find them? How does it affect our perspective on reference points? There was a suggestion that the biological reference point should be estimated within the assessment model. Should we change our control rules to better address stocks in a changing climate? So that's an initiative that the New England Council is undertaking now. And there's our research track assessments underway for winter flounder and also for American lobster, where the productivity appears to have changed. You can see that they're different. Well, first of all, for Atlantic herring, you can see that this assessment scientist has fit different windows, breakpoints. And the thing I really want to point out is these breakpoints are based on the recruits per spawning stock biomass. So that's really important, that if a breakpoint analysis is used, it should really be based on the recruitment rate rather than the recruitment per se. The problem with using recruitment per se is if you have low recruitment, how can you be sure whether it's because the productivity has changed or whether you just don't have enough spawners? So this is one point I'm going to come back to. It should be based on the recruitment rate. We can also see the productivity periods for American lobster, and that benchmark is going on now, and that's one of the reasons that Connor can't be with us today. He's at the lobster benchmark assessment, where they're dealing with similar issues of changing productivity regimes for lobster. So I think that, I think that wraps up this segment of the presentation. So probably a good time to break for questions, especially ones that are specific to these slides in this presentation, which I hope I've done justice to.
Well, I think this is a great slide to end on. It has a lot of questions for the audience, and I feel like we are dealing with some of these exact same points that you're talking about, where we're seeing changes in, unfortunately, we have it per se recruitment. We don't have juvenile studies to get us down to the juvenile stage of many of these fish, so it's hard to observe the rate. But I'll leave that up to other folks to ask questions on. So if anybody has a question, please click on the icon that looks like a hand-drawn hand or a turkey. Once it turns green, that's an indication, or once it turns red, that means your hand is raised. And then when I unmute you, the webinar will notify you that you've been unmuted, and then just click on your microphone, and that should turn green so we can hear you. And our first question is from Brendan Rundy.
Thanks, Chip. Thanks, Dr. Colley. That was an interesting presentation. This is Brendan Rundy with the Nature Conservancy in Virginia. I wanted to ask about this idea of breakpoint analysis and using, in the case of the Atlantic herring plot here, a measure of recruitment per biomass in different time periods. In the South Atlantic, you may know that red snapper is perhaps our most contentious species, and there is an amendment right now to the fishery management plan that is under development for red snapper that would potentially use the recruitment for that species that's been estimated over the most recent 10 years. It's been very high recruitment relative to the long-term recruitment going back to the beginning of fisheries time, which is the early 1980s. So my question is, can you talk about the difficulty in deciding whether to use the long-term average versus a recent period, and what the risks of that may be from a conservation standpoint or a precautionary standpoint? Thank you.
Yeah, thanks very much for your question, Brendan. And that echoes, I think, the discussions that we're having on these stocks and others is about whether it's appropriate to use recruitment windows and then how you find them. I'll just list some of the challenges, and I'm going to leave what I consider one possible solution to the second part of my talk. But I think some of the challenges with estimating recruitment windows are as follows, and I'll list off a number. One of the things is like, are we changing the goalposts? Can some of these stocks recover if given a chance? So there's that one. There's a problem of identifiability. Different algorithms give you different breakpoints, and how do you know which one to believe? There's another problem of how do you know how long the current regime is going to last before it may switch into a, switch back or into a new regime. So there's the problem if you're making projections, you just assume that the current regime will go on forever. So that's a challenge. And then another one, maybe the last one, is that in some cases, there do seem to be sharp breaks. In other cases, the changes in the recruitment or recruitment rate seem to be more kind of gradual, and there's no clear definition. And so, I mean, even this one for herring, we had this low regime. I'm looking at it earlier too, but yes, we still had some very strong year classes. So it's possible that for some of these stocks, the dynamic is not really discrete regimes. It could be a more continuous type of pattern. And the final one that I was trying to remember here is the final risk is that by just using the most recent, say 10 years, like, are you just discounting everything you learned up until that point? Like, we're not using those data. And if those data from before actually tell us something, inform us about the actual population dynamics of the red snapper or other species, it seems like we ought to be using them to understand the dynamics better. So that's my litany. I'll stop there.
All right, Wilson has his hand raised.
Thank you, Dr. Collier. Jeremy, this is Wilson Laney, formerly of the U.S. Fish and Wildlife Service, now of NC State University. My question is maybe a little bit off base here. You noted the temperature relationship in terms of winter flounder recruitment. Is anybody looking to see whether or not any of these stocks that are adversely affected by rising temperatures are showing any indications of genetic adaptation to a higher temperature regime, and whether or not somehow that could be factored into the likelihood of stock restoration?
Yeah, thanks, Wilson. No, that's a really good question. I don't think it's off base at all, because it's really relevant as to whether, these stocks are kind of frozen in place in time, or whether there is some adaptability. And I don't think I can give you a full answer, but I can give you a little, maybe a little hint. I know that people in Atlantic cod are studying the genetics quite carefully, and because the cod stocks in New England have just been redesignated, the stock structure has been reevaluated. And among the genetic markers, I believe is a genetic marker that is actually like a coding gene that is related to temperature tolerance. So that definitely that could be going on. Whether the adaptation can occur fast enough to keep up with climate change, I guess, is another question. But thanks for your question.
Yeah, thank you very much. Appreciate that.
So I'm not seeing any hands right now, but I'll ask a quick question. Much like you're presenting down there for American lobster, the red snapper is having that increased trajectory, and you also have Atlantic herring on there. And to me, it's interesting on the different dynamics that you have to approach these two different stocks with. It seems to be much easier to control fishing for a negative population growth, right? Because we have to avoid overfishing, and so you can down from whatever FMSY is to a certain level. But if you have a population that's doing better than normal, how do you begin to develop a FMSY or a FMSY proxy in order to avoid overfishing when it might be the last 10 years like you do have for American lobster down there?
Yeah, thanks. Sorry, I'm not sure I quite caught your question. Was the question like, what do you do for stocks that are actually in a high productivity regime? How do you manage those to prevent overfishing?
Yes.
Okay, great. Yeah.
Good translation.
Yeah. I mean, an American lobster in the Gulf of Maine is maybe a really good example of that, in that there's been just a bonanza of lobster catches in the past decade. But already we're seeing signs of a downturn in the Gulf of Maine. And I think that's what the Lobster Board is kind of going to be dealing with, is how do they deal with this proactively? Because clearly in Maine, the lobster industry has really developed and is highly dependent on the lobster catch. So, on one hand, you could argue that, well, in the boom times, we should be able to take advantage of that. But I think that there needs to be some kind of proactive harvest strategy. And American lobsters, I think, is a challenging one, because there's only input controls, there's no output control, and so there's not really a fine precision of management on lobster, and so the risk is that they will act too late.
Any other questions before we go into the next presentation?
Okay, let me escape out of this one. And so shall I go ahead with part 2?
Yeah, let's go ahead with part 2.
Great. Okay, well, again, thanks for your questions, and I'll try to think about them as I'm presenting. So this was based on the keynote talk I gave at the National SSC meeting to try to set the stage for possible strategies that could be dynamic or climate resilient for marine fish stocks. So I'd like to acknowledge my co-authors, Rich Bell, who works for TNC, Colleen Minto from Ireland, Paul Spencer, NOAA Fisheries in Alaska, and Rachel Marshall, who is my PhD student here at URI. And so in this project, the steps were, we want to examine the evidence for changes in recruitment productivity in US fish stocks in 5 regions of the US, search for environmental covariates to explain the observed changes in productivity, calculate dynamic biological reference points, and then evaluate the performance of dynamic harvest control rules, and to really think about the results in light of what we know about harvesting theory. And so the question we asked is, like, if we followed these steps from 1 to 4 and 1 to 5, what would a dynamic harvest control actually look like, and how well would it perform relative to our status quo time invariant harvest policies? And so in the next set of slides, I'll come back and try to answer that question for you. So just to look at the big picture first, we're looking at, I think, 84 stocks that have age-structured stock assessments from 5 regions of the US. You can see the 5 regions there. And what I've shown is, of those stocks, how many of them we would designate having time-varying productivity. And I'll explain what our test is. But you can see here a couple of things. One is that the proportion of stocks with time-varying productivity is higher on the East Coast than the West Coast. And that's really an interesting question. And there are 2 potential reasons for that. One is that on the East Coast, we've just fished harder. And so there's more contrast in the spawning stock biomass level. So maybe we're just better able to detect time-varying productivity in our models relative to the West Coast, where the stocks have been more lightly fished, you could say. The other explanation is that the climate or environmental influence on the West Coast is different than on the East Coast. On the East Coast, we may have these decadal changes in productivity that we've seen, whereas in the West Coast, the effect of the oceanic environment may be more high frequency and not longer term. So that's a really interesting hypothesis that we've noticed, but I don't think we've fully answered yet. The other thing you may be very apparent to you down south is we don't have any stocks from the South Atlantic or Gulf of Mexico. And I guess maybe we were afraid to get into the red snapper or something like that. But I think the real reason we don't really have any colleagues or collaborators on the project from there, so we didn't do it. But it's not for lack of interest. So maybe that will be a follow-up. So going from the big picture, this is from Rachel's recent paper, I want to focus on a couple of stocks in the New England region. So if we look at the New England region, and first of all, define what we mean by production. So fish production has different components. One is recruitment, we keep track of growth, maturity, and fecundity, all determine the productivity of the stock. Fecundity is in gray because often no one wants to count fish eggs, so we assume it's constant. Where there are changes in growth and maturity, we account for them. But recruitment is bolded because most of the variability in fish stocks is due to variation in recruitment or recruitment rate. So that's why it's bolded there. And if you look at the patterns of productivity in for these dozen New England stocks, and over time here, the y-axis is productivity, and the units are really log recruits per spawner. So just think of this as the recruitment, per capita recruitment rate. And we have one pelagic species, we have these demersal stocks, then we have a number of flatfish species in pink. And you can see they display a variety of patterns. You can see there's a stock here, Acadian redfish, which increased in productivity. You see these decadal patterns like our haddock. And then we see these declines, especially for the flatfish stocks. For many of these stocks, we do see a little uptick in productivity in recent years. So that's, of course, highly uncertain, as we know, but I'm still tend to be a little cautiously optimistic about that. So I'll explain how these are estimated in a minute, but if you just look visually at the patterns, you can see that, for the changes are kind of gradual. I think they don't really look like step changes for most of the species. So I think that challenges our idea that there's clear breaks in productivity. It's kind of up and down, but not any clear breaks. So that's a challenge. The value of this type of analysis, I think, is that we can then say, if we've seen a shift in productivity, at least we can say whether it's something that happened before recruitment, since these are recruitment data, or maybe it's something after recruitment, maybe it's growth or maturity. So it gives us that kind of diagnostic test of where in the life history of the species this change is occurring. So the stocks I'm going to highlight now is the white hake, because that's one we've been debating in the SSC. The winter flounder from the Georges Bank region, we're going to highlight that one as well. I could talk about winter flounder in the Southern England stock. This is based on Connor slots, but we kind of avoided that because I didn't want to really, since I knew Connor was going to present that already. So now I'm going to get into a little bit of methods. So I have one kind of heavy data slide. I'm going to walk through this slowly. So this is what the model we actually fit, and it's a dynamic version of the Ricker model. So I think you all in fisheries science are familiar with the Ricker model. In its linearized form, it looks like this, where A is the per capita recruitment at low spawning stock biomass, and B is a density-dependent parameter, and V is some kind of uncorrelated random error. So that's the typical time invariant Ricker model. We can fit a time varying version of that by making this productivity parameter, AFT, vary over time. And it's modeled as a random walk and as a process error, W of T. So instead of being fixed, this parameter is changing over time. And the parameters are estimated with a Kalman filter, the linear state space model. We can use the DLM package in R, producing the time series of AFT and its associated uncertainty, which I showed you in the previous slide. And we use a likelihood ratio test for model selection. So we're not just saying, well, we're saying that all these stocks are time varying. We're actually testing one model against the other to see which one has the most support. So in the example I gave you, and I think I can just go back, these stocks we would say are all time varying statistically, except for American Place, where the best model was time invariant. So that was the lone one here. And you can kind of do a visual test. Like if you could fit a horizontal line through the confidence interval, then you would say maybe that's time invariant. Like if you couldn't, then that would be evidence for time variation. So that's how we fit the model, and that's our test of whether the dynamics are time varying or time invariant. Okay, so for the dynamic models, one benefit of that is we can have improved recruitment forecasts up to 3 years in the future. And so these bars are comparing the time varying model compared with the time invariant model. And you can see for most of these stocks, there is an improvement in forecast gain for up to 3 years. And a big reason for this is that if we're starting now and projecting 1, 2, 3 years in the future, it really matters where you start from. And I think we can see this back here, where for a stock that's at low productivity and we're trying to project forward, we don't assume that the productivity is going to be the average over the time series, because we would lead to overestimates. And that's been a problem that just plagued us in all our short-term projections. Whenever we make a projection of what's going to happen 1, 2, 3 years or rebuilding, we're just chronically over-optimistic. And then next year we say, oh boy, we were over-optimistic, and we reset, and then we're still over-optimistic. So starting from a more realistic starting point then gives you a better short-term projection and a more realistic rebuilding scenario. So that, I think, is an important point in the short term. Of course, it would be nice to be able to explain these patterns, and for the winter flounder, I just want to point out that for our target stocks, we do see improvements in recruitment. To try to explain these changes in productivity, we, and especially my student Rachel, are fitting environmental driven recruitment models. So here we have 3 different hypotheses about how the environment is actually affecting dynamics. And we enter the environment E into the process equation. Here, the variable is entered itself. In hypothesis 4, it's the change in the environmental condition that is affecting productivity. And then we can put the environment right into the observation equation here. So you can think of this as a more standard environmental driven Ricker model. And then we estimate these D parameters. You can see they're color coded, so they correspond to the effects. So for our 2 example species, for white hake, you can see there's a negative effect of the Arctic oscillation, negative effects of bottom temperature, and for the winter flounder, negative effect of bottom temperature and negative NAO. So we do see significant environmental correlates, and the idea is that when we fit this environment dependent model, how much of the variance can we explain with this covariate versus the unexplained variability? The idea is if the environment is really important, we're going to see more of the effect attributed to the environment, and this WT variance ought to be smaller. So that's the hypothesis. And so we do see significant environmental effects for some of the stocks, not all, but for many, and for some of them, like winter flounder, we actually have a hypothesis. We say, okay, it's the winter temperature that's important. We know that. For many of these stocks, that we really don't know what the mechanism is whereby the environment is affecting the recruitment rate. But even so, we have to move ahead and manage the stocks. putting this in a management framework, I think those of you who work in management would agree that it's much easier to convince a decision maker to make some change if you can explain what the mechanism is, rather than just saying, well, oh, productivity's gone down, we need to adjust our harvest rate. I think most decision makers would be more confident if they actually knew what was going on in some underlying process. Even so, though, we can use these methods to move ahead and calculate dynamic reference points. So that's shown here. This is for white hake. You can see I'm jumping between white hake and winter flounder, but I think at the very least I identify which species I'm talking about. So I hope that won't be confusing. But here's how the rationale works for white hake. These are the stock recruitment data over time, and you can see it's a long time series. And so we have actually good contrast in these data, which gives us the ability to estimate the time varying models. The estimates of productivity here are shown in panel B, and so you can see productivity was high, and then it dropped down to lower levels more recently. And so when we fit the reference points, the FMSY and the SSBMSY, we fit them under 4 different assumptions, because we want to say, well, what makes the most difference? So the red line is static growth and maturity. So obviously the reference, we're assuming the recruitment rate is constant, and so the reference point itself is going to be constant over time because nothing's changing. We can add in dynamic growth and maturity. That is, we're accounting for changes in the growth rate and maturity. And so that changes the reference points a little bit, but you can hardly see it for the SSB. So it's changing a little bit. By contrast, if we account for this variable per capita recruitment, that is the blue line here, you can see that the FMSY kind of mirrors that pattern, and it changes a lot over time. If we also account for dynamic growth and maturity, those lines are very much the same. So whether or not we account for the dynamic growth and maturity is not having a big effect. It's the dynamic reference points depend more on changes in the recruitment rate than on growth or mortality. So that's the conclusion here, and that's we kind of labored the point here to make that. And the dynamic reference points that we calculate could be quite different than the proxies that were used in the stock assessment. You can see for this case for white hake, the FMSY proxy was actually quite a bit lower, and the SSB MSY proxy was much higher. And so that's saying this is kind of our rebuilding target when the dynamic models say, well, no, actually, it's not that high. So that makes a difference, as you will see. So we have dynamic reference points, and we can expand this to other species or stocks. And so if you think about how much is this reference point changing over time, we can plot it as a box plot. Here's the one for white hake here. You can see this is just how much that dynamic reference point would change over time relative to a static reference point. And the point we're making here is that the violet and cyan boxes are much wider than the green ones. Red, it would be the static reference point. And so we're saying that a lot of the variability in dynamic reference point is due to the recruitment rate. Now you see that even more so for winter flounder, that the purple bars and blue ones are bigger than the green ones. So again, we're making that point. And the other point here is that the variability in the reference point, it's greater for FMSY than for SSBMSY. So you can see that looking at the x-axis range, there's a bigger range in FMSY than there is in the SSBMSY. So we should really pay attention to the fishing mortality rate target. So we have these dynamic reference points, and then the next question is, how could you use them? I mean, if you really think that the reference points are changing over time, how could you change your harvest strategy to account for that? And so one step on this was to actually find out what the optimal harvest control will be for a time-varying stock or non-stationary stock. And we answered this with dynamic programming, or stochastic dynamic programming, which is an optimization tool, which I think is maybe a little bit underappreciated. But basically, dynamic programming, if you have a objective function, which in this case is obtaining maximum sustainable yield, it will tell you what's the optimal harvest rate for every combination of biomass and productivity. The colored lines here are the productivity levels. And dynamic programming then gives you a harvest control rule, which looks like this, that as biomass, I'll look at the middle one. So look at, as biomass goes down, the harvest rate also declines until you get to an intercept here. And so, I mean, it's well known through harvesting theory that the optimal policy to achieve MSY is just to get to MSY as quickly as you can, because that's going to be the most productive level. So the MSY reference points are shown here with the dots. So this is BMSY, that's the harvest rate for MSY. And this harvest rule will get you there as quickly as possible in one time step or multiple time steps for rebuilding. So the colored lines then are correspond to different productivity levels. So you can think of this as a family of curves. There's a different curve for each productivity level, going from low in red, high in blue. And for each one, there's a corresponding pair of MSY reference points. So as productivity declines, the BMSY is going down and the harvest rate to achieve BMSY is also going down. You get to here where there's barely a sustainable fishery. There's just a very small harvest rate and a very low biomass. And maybe we have some stocks that are kind of in that region there. So this sometimes is a little bit counterintuitive, because you would say, well, why, if you have a low productive stock, why would you harvest it so hard? And the idea is that if for some magic reason your stock was way up here and the MSY is there, obviously you would get there quickly, because that's not a sustainable, that's not going to be a sustainable harvest, because the BMSY is way down here. So I think that the optimal solution is very useful, because it tells you what in that situation what will be the optimal harvest rate, and we can kind of pattern our realized harvest control rules based on these principles. Of course, the realized harvest principles are not like this, because basically the harvest control rules we use now say you can't harvest above FMSY ever. You have to stop there. So they don't allow you to harvest down any surplus. But I'll just end, before I move on here, I'll say that, repeat, the optimal harvest policy adjusts the stock to its MSY level as quickly as possible while anticipating future changes in productivity. And the anticipating is important, because you don't need to know what the future is going to bring, because the dynamic programming has basically iterated over all those possible outcomes and is telling you what the best harvest policy is now, based on the current condition. And so the way this would be used operationally would be, say, well, in a given year, you'd say, okay, this is our biomass. This is the productivity level. So you go up to that productivity line and say, that's the harvest rate that we should use this year. And then it's predicated on the assumption that next year, you're also going to assess the stock and the productivity, and you would choose the appropriate level in the following year. Okay, well, that's quite a mouthful. And I can't really explain dynamic programming on the fly here, but if anyone's interested in it, I just refer you to our paper, or I'd be happy to answer questions about it. But we realize that, the real harvest control rules that we use are not optimal in any sense, although they do try to achieve maximum sustainable yield. But to really be relevant, or to provide some management on-ramps, we should look at the harvest control rules that we actually do use, and then think about how they could be adapted to be made more climate adaptive or resilient. And so the types of harvest control rules are used in practice. This is an example that would apply, say, in the North Pacific, which I think you're familiar with. We could call this a rectilinear harvest control rule, or state-based, because it's based on the abundance of the state of the biomass, or ramp. Sometimes we call them ramp, or Canadians might call this a hockey stick. Anyhow, you get the idea that there's a maximum, which is based on MSY or its proxy, F35%, and there's a hinge point, which could be BMSY or its proxy, B40%. Beyond, after that, the fishing mortality declines linearly to 0 or a point near 0. And I want to point out that we're really dealing with the overfishing levels here, not the ABC. So we're dealing with the red line, not the green line. The green line incorporates uncertainty buffers, and you can see that in the North Pacific, they have this kind of uncertainty buffer. But we're really talking about the red line here, the F overfishing level, which corresponds to MSY. So then you can ask, well, okay, we have this control rule. How could that change over time? And so we can think about different possibilities for that, given that we have dynamic reference points. So this shows the different harvest control rules that we actually simulated and tested. So in each of these subplots, we see the dots are the estimates of the dynamic reference points. So that's the dynamic BMSY and dynamic FMSY co-varying over time. And in this case, it's kind of a banana pattern. And the reason it's a cloud and not a curve is because it also accounts for the changes in growth or weighted age over time. But this cluster is repeated in each of the four subplots. And again, FMSY and BMSY co-vary with this relationship. So superimposed on that are the types of harvest control rules that we could use. The simplest is just a constant fishing mortality rate, the black line, or we could have a constant control rule, the purple line with a hinge point at some kind of medium FMSY, BMSY, so that's the purple. Then you can say, well, what if we made it time varying? If we make the fishing mortality rate time varying, we have a different horizontal line for each year, which is kind of confusing. But I've highlighted every 7th year here in color. So we go from blue, 1963, up through the purples and back to the red. So it's actually kind of changing gradually over time. I've just plotted every 7th value. And see, the idea is you choose the horizontal line for that year or that assessment. Then the final one in D is to actually have a time varying harvest control rule, where in addition to the horizontal lines changing, we have we also have varying hinge points at FMSY. So you have a family of harvest control rules. And again, you can see how these co-vary. And so it doesn't make sense to change BMSY without also changing FMSY. And I think I highlighted something that if it doesn't make sense to change one, like this horizontal line, without changing or decreasing FMSY. And this is the problem that we really encountered for many stocks, and this is the problem that was encountered for the crab in the Bering Sea, that the idea that it could lead you to an actual higher harvest rate if you didn't actually reduce FMSY at the same time. So that's going to, this purple dashed line is actually really risky. So we wouldn't want to do that. So the idea behind these 4 different harvest control rules is now we can make a contrast. We can contrast between having just a constant F strategy and a harvest control rule, a ramped one. So also C versus D. And we can make a contrast between having a stationary or time invariant harvest control rule versus time varying, or a time invariant harvest control rule, like B versus D comparison. So we can see which makes the most difference in our management performance. So I'll just explain briefly how this simulation works. We simulate the age structured population over the same time horizon as the stock assessment. So it's kind of like a what-if simulation. We generate recruitment with a time varying Ricker model based on the estimated productivity time series in random measurement areas. So the time varying Ricker model is basically our operating model. If that were the state of nature, what would happen? I explained the 4 harvest control rules, so I probably don't need to repeat that. Then we compare the performance of the harvest control rules based on various measures of catch and catch variance, spawning stock biomass, etc. And we've really accounted for the main sources of variation. So I've highlighted these ones the process error variation, that's the change in productivity, and the observation errors, which is the unaccounted for variability in recruitment, which is also quite high. So here's an example of the simulation, and this is kind of a busy plot, but I'll walk you through it to make the main points. So this is the simulation for white hake, and so the simulation is driven by the fishing mortality rate. The recruitment is a function of the productivity, so you can see it was high at the beginning and then declining. As a result of that, of the fishing mortality, we get a catch over time and the resulting spawning stock biomass. These quantities are plotted relative to what was observed. So the observed is what was estimated in the stock assessment. And we just wanted to show this mainly to show that the simulated values were within the range of what has been observed over time. So they weren't completely, off the scale of the stock. And you can see that's the case, especially for recruitment. You can see these uncertainty intervals basically bracket the range of observed recruitment. So we know that our scaling is more or less okay. One could also ask, well, if you followed a time varying policy from the very beginning, how well would you do? How much better could you do relative to the decisions were made at the time? But I think that's kind of a secondary point. Okay, now I'll just talk about the different. We have these 4 different harvest policies. We have the constant F, that's the black. We have a constant control rule. It only reduces the fishing mortality when the spawning stock biomass declines. We have the time varying FMSY policy. So it's high when productivity is high and then it declines when the productivity goes down. And then we have the time varying control rule, which is the green. So you can see that the control rules are doing what they're supposed to do. When biomass is low, they reduce the fishing mortality rate because of that ramp function. But it's kind of subtle here. You can see it's only happening in some years and not others. There's great uncertainty or a wide range of fishing mortality rates, because when you think of being a simulated manager starting back in 1970, you only have a few years of data. You don't know what the productivity is, so you don't really know what FMSY is. And that's actually captured here because we have this wide, we're resampling from the Coleman filters. We have this wide uncertainty interval in knowing what the FMSY actually is and the BMSY. Nevertheless, you can see that the median of the FMSY tracks the estimated value really closely. So it means that our estimation is it's uncertain, but it's not biased. So that was kind of reassuring. So in this scenario, so recruitment is driven by the productivity time series, and it's a little bit higher for the time varying models because it keeps the stock in its productive level of spawning stock biomass more than the time invariant one. The fishing mortality would be higher than this F40%, which is, as I showed you early, is actually fairly risk averse or conservative. As a result, the catches are higher for the time varying policies. They're kind of tracking the dynamic MSY, not exactly, but they're kind of tracking that. And then we look at the spawning stock biomass. The time invariant policies are basically have higher spawning stock biomass because they're not fishing very hard, whereas the time varying policies are tracking the dynamic BMSY more closely over time and ending above it. So that's kind of how the simulation works. And of course, it depends on what the time invariant harvest rate is. This one is pretty risk averse or low, and so it's foregoing catch. By keeping spawning stock biomass high, it's foregoing catch, at least in the early years. So one might ask, well, what if you basically had a higher, more aggressive fishing mortality rate? And we can look at this by looking at the next example, which is for the winter flounder, where the F40% is actually higher, and it's more in line with the dynamic FMSY. And I don't think I need to repeat all this because I just explained it all for white hake. But the differences I wanted to point out were that because of this, there's not much difference in catch in the time invariant and time varying harvest policies. You can get the same catch either by fishing a higher spawning stock biomass at a lower fishing mortality rate, or fishing harder with a lower spawning stock biomass, you get about the same catch. So the benefit of the time varying policies is not here in increasing the catch. The benefit is when productivity declines, the fishing mortality rate is reduced substantially, and the spawning stock biomass is maintained further above its dynamic target value. So it's really in this area that the time varying harvest policy is really performing well. And of course, this is where we are, and this is the area we're concerned in. You can see that the time invariant harvest control rule, the purple here, is reducing fishing mortality rate, but not fast enough to get it down to what the dynamic FMSY would be. So it's helping partially. So I realize there's a lot going on here, and we kind of struggled with how do we summarize this. And one way we tried to summarize it was saying, well, what if we look at the difference between the time varying and time invariant policies, like this difference, and this difference could be negative or positive. But instead of looking at it over time, looking at it as a function of the productivity itself. So in this next plot, I've basically taken these trajectories and plotted the differences as a function of the productivity. So the x-axis is just the Richter A value from low to high, and then we have the difference in fishing mortality, difference in catch, and the difference in spawning stock biomass. And I can summarize this at low productivity down here, the time varying harvest policies, they reduce fishing mortality and catch while maintaining higher spawning stock biomass. So they're both performing well at low productivity. The time varying harvest policy also takes advantage of high productivity, increases fishing mortality and catch, and but note that the spawning stock biomass would still be maintained close to its target value. The reason this is below the zero is because the time invariant policy is basically foregoing catch at high productivity. And the final point here is that the time invariant harvest control rule can compensate for changing productivity to a limited degree. So that's the difference between the asterisks and the dots here. You can see that it's kind of bringing it down, but all right, yeah. Sorry, I guess you could say it's bringing the fishing mortality rate down and increasing the spawning stock biomass, but not to the extent of the time varying harvest policies. So just to kind of try to reinforce this, basically what we're saying is that when we make these comparisons between, we see pretty small differences between the harvest control rule and the F-based rules. We see big differences between the time varying and the time invariant harvest policies in our results. Okay, so I'll just kind of start wrapping up here. One question is it better to have a robust harvest policy or one that is adaptive or resilient? And this has been a topic for several decades, and I just wanted to highlight a few papers about this. This paper by Walters and Parma was really an important paper, I think, and it was based on stochastic dynamic programming. And they said that when climate impacts produce strongly autocorrelated interannual variations in recruitment, harvesting a constant fraction of the stock allows the spawning stock to track such variations. So they're really advocating that in the face of this climate variability, to just stick with a constant F strategy. Another more recent paper, Robust Fisheries Management Strategies Under Deep Uncertainty. I thought this was an interesting paper, although the method, I don't know, maybe hard to follow. But one quote I thought was really interesting here, where they said that model-based projections of fish stocks are severely limited by large uncertainties in the recruitment process. An alternative is to shift focus to improving the decision-making process by identifying management decisions that are robust to a vast range of uncertain scenarios. And I certainly agree with the first part that we recognize that projections are severely limited by large uncertainties in the recruitment process. We have very limited ability to project, actual recruitment. And so they're advocating for more robust strategies. that was a little bit different from our own conclusions in our paper, where we said that the priorities for managing fish stocks influenced by climate change are first to measure the current productivity, assess the current state of the stock, and then respond with a dynamic harvest control rule of the type that I just illustrated. And so those were our main conclusions. And so it kind of begs the question of like, when is a robust harvest control rule, would it be preferable? You know, when is a climate adaptive or resilient one desirable, and when is it even possible? And I think one key determinant here is the amount of data that are available for the stock. The stocks, you know, I showed you, I think have age structured assessments, and so they're fairly data rich, and so we can actually estimate the time variation productivity. By contrast, stocks that are more data poor or data limited, and I know there are quite a few of those in the South Atlantic, it's hard to even estimate reference points at all, and so it's unrealistic to think that we could have some kind of dynamic reference point. And so in those cases, it may make more sense to kind of find harvest control rules that we consider to be more robust to environmental change. But I think that's an interesting and open discussion. So I can see it's after 2, so let me wrap up here. So I've shown that there is strong evidence for decadal changes in recruitment rate, what we are calling productivity, in the US regions and also in the general ICES area. Similar studies have been done in the Celtic Sea, for example. Some of these changes can be explained by environmental covariates, but for many of the stocks, we still don't know what the mechanism is linking the environment to recruitment. Nevertheless, time-varying recruitment models can provide improved recruitment forecasts from 1 to 3 years in the future, so that's useful for short-term projections. They also imply that there are corresponding changes in dynamic biological reference points. The dynamic reference points can in turn be used to construct dynamic harvest control rules, and such control rules can gradually adjust fishing pressure in response to changing productivity. An emphasis here on the gradually, because I think that's important, that rather than waiting and making some kind of abrupt change in the policy or the overfishing levels, that in principle, this type of dynamic model and control rule could actually be changing things gradually as time progresses. So that's a potential advantage. So with that, I'll wrap up here, just acknowledge the funding sources and the contributing institutions, and welcome any questions that you have.
Thank you for that great presentation. I'm going to take back control. I've got the slides, so I can come back to them if there are questions on certain ones. So, all right, just a quick description on how to operate the webinar. Again, you can enter a question into the question box. Might be varying depending on which platform you're using, webinar or installed base. To raise your hand, click on the hand icon, and then if it's green, that means your hand is down, red means raised, and then once again, click on the red microphone to unmute yourself. You'll be prompted to unmute yourself after I click on a button to unmute you. The webinar will let you know you've been unmuted. So with that, if there's any questions, please go ahead and raise your hand. And while folks are looking for their hand, I have a quick question. I noticed in the time varying recruitment, you had limited it to 3 years. Was that just based on the study that you guys did? You only looked at 3 years, or did it become, were there issues after you went past 3 years for that recruitment estimate?
Yeah, thanks for the question. So just to repeat it, so in making short-term projections, we cut it off at 3. We could go longer, but I think with any kind of time series modeling, the ability to make predictions really degenerates quickly with time. And so, you know, probably as you go in time, the uncertainty interval increases quite a bit. And so that's why one reason for limiting to 3 years. The other reason is that, at least in New England, we often make our projections for 3 years. So we're kind of setting ABC levels for 3 years at a time, anticipating that after 3 years, there'll be a new assessment. You know, sometimes the assessment frequency is more rapid, and so we're updating after 1 or 2 years, but it's probably 3 years is probably a realistic horizon for short-term projections.
Thank you. Yeah, in the South Atlantic, I think the SSC recommends 5 years post terminal year of the stock assessment, but we don't always get the next stock assessment after that 5-year mark, so we can be stuck at a constant point after that. I'll ask another question. I guess one of the concerns that we're worried about with some of these is how to, if we're not getting the updated information that we need every 3 years, like you're recommending in your paper, what is the process, or how do we highlight the need for looking at different species? Let's say, I mean, would you recommend species that you're seeing a signal in decreasing or increasing recruitment? Would you recommend those species be reassessed more frequently than species that maybe seem to have a constant level of recruitment?
Yeah, thanks for that question. The question is really about assessment frequency, and you know, how do we balance the number of assessments versus the number of stocks, and then more importantly, the number of assessment scientists to do the work. So it's always, and so in the simulations that I showed, you might say, well, that's kind of a best case scenario, because we're kind of assuming that there's recruitment at age 1, and we're doing a stock assessment every year. So that's maybe the best case scenario. And in New England, we don't do that. But I would point out that in the North Pacific, there are stocks that are assessed annually. So they basically, you know, they're doing it. And because those are, I guess, really important stocks, they're high valued, and so they put resources into it. And so I think that's an important trade-off. I think a general conclusion is that when you have non-stationarity or time variation, it's probably better to assess more frequently, but less thoroughly. Like, try to have some kind of assessment. I think, and we call them management track assessments, where they just kind of add the data and turn the crank and get an answer, rather than going through all the steps of the stock assessment. So, you know what, I realize that there are limits to personnel, what they can do, but it really does point towards having more frequent and maybe less intensive assessments.
All right, we've got a question in the question box. Let me pop it out so I can read the whole thing. When fitting the time varying recruitment models, did you notice any improvements in its fits and ability to estimate parameters, which might suggest misspecification in the current assessment models?
Okay, well, I think that's kind of a two-part question. I mean, the second part maybe I'll address first, about misspecification in the current assessment models. I will say that we're actually fitting these models to the output of the assessment. So we're assuming that the assessment is the best estimate of what the abundance is. And so we're not in a position to evaluate whether there's any misspecification. So I'll just say that. And well, maybe I'll come back to that one. That was part 2. Certainly, as I explained, the first part of the question was when we fit the models, you know, we're actually improving the fit with a time varying model. An ancillary question is, well, like, should this all be incorporated into the stock assessment model itself? Should we be estimating the time variation parameters in the stock assessment? And some people advocate that, and there are reasons why it'd be a good idea, and there are probably some reasons why might not be such a good idea. And we've actually done it both ways to see how much difference it makes. And we concluded it doesn't make a big difference. But we're not really, evaluating the stock assessment itself. We're saying that whoever did it, this was the best job they could do with the data they had.
Any other questions? I thought I saw a hand go up for a second.
Well, while you're waiting, I'll just comment on the slide that we're looking at. I assume everyone's looking at it, about the white hake productivity. Another development has been to develop a time-varying Beveridge-Holt model that people ask, well, why the Ricker? For many stocks or some programs, you actually assume a Beveridge-Holt model. And the answer is you can fit it in time-varying fashion, but it's more difficult. And often you see similar patterns in productivity as shown here for white hake. And my colleague Colleen Minta was just finishing a paper where he describes how to fit a time-varying Beveridge-Holt model. So we think that'll be a really nice addition to the field, the ability to do that.
And sorry, I didn't mention this earlier, or I didn't send it earlier, but you talked about two different papers. So I'm putting your paper that you had mentioned, as well as a Zawalski paper in the chat. So if anybody wants to find them pretty easily, there's links to those in the chat. Any other questions? I know this is a difficult topic. It can be a challenge to understand well, and we really appreciate the work that you're putting in to really look into how to do this best and manage these stocks as we're going through some of these non-stationarity points. And some are going to be increasing, some are going to be decreasing, but managing these to a sustainable level, I think, is going to be important, and understand how to get there. And it's just been a little bit of a challenge, I think, in the different regions. So with that, I wanted to thank you.
I'll just say in ending, thanks for your attention. I know I presented quite a bit of material on that second part, maybe kind of rapidly, but I wanted to give you at least a flavor of what we're doing here and trying to think through what a time-varying harvest policy might look like. I know that we kind of ignored the South Atlantic, so if any of you see any kind of areas of uptake in the South Atlantic for any of these ideas, any of your stocks, I'd be happy to follow up with any of you to explain in more detail how our approach works.
Yeah, I think we are definitely going to be reaching out to you, and although Judd's not on today because he's at another meeting, he's likely to be reaching out to you to maybe give a presentation at the SSC meeting in the future. So thanks again. This was a great talk, and we're not going to have a seminar series next month because we have our council meeting. But following that, we're going to have a seminar on black sea bass in April, given by South Carolina DNR staff. And they're going to be looking into a bass model that they recently published, looking at the distribution of black sea bass, as well as some genetic work that they're doing on the stock, looking at how the genetics is changing along the Atlantic coast. There's two different stocks that we have on the East Coast, and just look to see if the South Atlantic is migrating more northward or what's going on with the population. Thank you all for attending today, and look forward to seeing you in April.
Okay. Thank you for moderating.